Okay. Right. So the other interval that we can use is called the highest density region. Right. It's actually a region that actually also contains 1 minus alpha 100% of the posterior distribution. Right. But the key point here is actually the density inside the region is never lower than outside. Okay. All right. So okay, when you say density, right? Okay, so if you look at the graph, right? Okay, so for example, you have this graph. Okay, so the density is actually the value of your function. Okay, so if you, for example, right, if you have your fx, right, or your your function of your posterior, right, then the height of the graph is called the density, right? This is the density, right? And but the area under the curve is actually your probability. Okay. So for example, right? So if you're looking at the density, then we are looking actually at the height of the graph, right? And inside the HDR, or the highest density region, is meaning that if you have an area, right? If you have the area inside the graph, for example, you have this area here, right? So meaning that this is your interval. Then the height outside of the interval is lower than, or sorry, the height inside the region is actually never lower than outside. Okay, so if you're looking at the height, for example, this is your region, the blue one, then the height of the, for example, the outside one is this one, this is the outside one, right? This is the height. So you can see the height of this graph here inside, right, is never lower than the height from outside. Okay, so this means that we have to make sure that when we when we find the region, the area inside here is still 1 minus alpha. The probability is still 1 minus alpha. But we have to adjust the percentile here. You have to adjust the percentile here such that the height of the graph, which is the density, from outside the region is never never higher than inside the region. Okay, so this will actually need you to do like trial and error, because this is no formula for this actually. Okay, but anyway, just take note, right? If you have a unimodal symmetric distribution, then the HDR and the credible interval are the same region. So what is unimodal? We have one mode and it's symmetric. So usually when you have normal, right? So if you have a normal distribution, then the HDR and the CI are actually the same region. But if you have more than one mode, or you have a non-symmetric distribution, then the HDR and the CI are sometimes or usually are not the same region. Okay, so you have to make sure. Okay, how do we actually do this? Is by try and error. Okay, so if you look at example, right, we have a posterior distribution given by gamma 2,3. Okay, you have a gamma 2,3, and you want to find the 90% credible interval and 90% highest density region. So this means your alpha is actually 10% or 0.1. Okay, then you have 1 minus alpha is 0.9. Okay, so here, right, so if I were to have a gamma distribution, okay, so this one is a simple, just a simple example, right? So how do we actually find, you can actually find the gamma percentile by using the R. Please make it larger. All right. So, right. So we have a, so for example, if I want to have a 90% creditable interval, right? So I will find so in this case, this is actually 0.12 and 1.56. Okay, you can see here, right? Then this is actually the percentile of 5, or you can use 5 or P5, and then you have P95, right? So if you look at the percentile here, this is your P5, and this is your P95, right? So if you have 95%, because we are using alpha over 2 and alpha over 2. So the region here, this probability is actually alpha over 2, and this probability, the white one, is actually alpha over 2, which is 5%. Right, so this is 5% of 0.05, the probability is 0.05. Then you have P5 and P95. Okay, so using R, you can actually find this percentile, and the red one is actually the 90% credible interval if your distribution is gamma to 3. Okay, so this is so as long as you use alpha over 2 for both sides, then finding the credible interval is not hard, as long as you have the distribution, which is the posterior distribution. Okay. But if you look at this credible interval, right, what if I were to choose 1 point inside and 1 point outside the credible interval, right? So P5, this is actually 0.12, right? And this is 1.56, right? The P95. Okay. So I choose, for example, I choose theta 1.5. Okay, so this is 1.5, this is 1.5 here. All right, and I also choose a value which is outside. So this is 0.12, so I choose, what if I choose a value here which is 0.1? Okay, so if I were to, so this 1.5 is actually inside the interval, and 0.1 is actually outside the interval, right? So if I were to find the property of theta, sorry, the density, not property, the density of the height of the theta when it's actually 1.5, right? Given y, so this is actually 0.15. This is this height, right? This height here is 1.5, and if I choose theta is 0.1, right? And the height is, so this is density, right? The height is actually 0.7. You can see right from here already. This is 0.7, the height, and this is 0.15. So the density of the inside the interval is actually much lower than density outside the interval. So this credible interval is not, here your credible interval does not equal to your highest density region. Okay, and this is because you can see the gamma is a very skewed distribution, right? It's not symmetric. That's why you have the credible interval is not equal to your highest density region, because there are a lot of areas inside the interval which is actually lower in density than outside the interval. Okay, then so how do we actually find the highest density region? That is a question where actually is by try and error. Okay, so by try and error meaning you have to adjust, right? So the easiest way is actually you have to adjust, because when you have the height, right, this is the density. So what you want to do is such that the density on the left and the right are actually equal in height. Okay, so what happens here is, if you look over here, right, you make a line. Oh, my line is, I think it should be lower than that. I think, yeah, because this graph is not very accurate, right? Okay, still not. Okay, my drawing is all right, something like that, right? So this is by try and error. Okay, by try and error. So we have this height. So to make it HDR, right? So with it's a try and error. With the 90% HDR is the area inside here must be probability 0.9. Okay, but you can see the left side, right? The left side and the right side, they are not the same size. Okay, because for HDR we don't care about that. Okay, and here this is actually 0.03 and 1.28. Okay, and so you can see over here, right, the probability of x between 0.03 and 1.28 is actually not exactly 0.9 because it's very hard to find exactly the value. So I get 0.89, which is close to 0.9. So this is actually using this value, I get 0.89, which is approximately 0.9. Okay, but you can see over here, right, if you draw a line here, then the area in the white area, which is outside of the interval, the red one is inside the interval, then the height of what is inside the interval should be at least as high as the one outside the interval. Okay, so biotarian error, so meaning that you have to adjust the height, which is h here. You have to adjust the height here such that, you know, the area here, the area under the curve in the red one would be approximately, in this case, 90%. So this one, you can, there's no formula for it. It's just try and error actually. Adjust. Okay. Right. So here, then you have to find, so this will correspond to some percentile, right? Okay, so you have to adjust and then go up the height, go you know, to the left, to the right, and adjust the height. Then only you can get approximately 90%. Okay, but the important part here is the height of the white part should never be higher than the height of the in the red region, which you can see, right, from the example here, from the CI here, right? You can see that even over here, a lot of the areas in the right side is actually lower than the area in the white part in the left side. So clearly, because it's a skewed distribution, then the credible interval is obviously not a highest density region. Okay, so the credible interval is actually easier to find, right? Because if you look over here, the HDR is actually harder to find because it's mostly by try and error actually. Okay, so what is the advantage, right? If you were to use the HDR, okay, the important part is for if you look at the multimodal distribution, right? For example, in here, okay, right? So if you have the credible interval, so this is your credible interval. Because, for example, you have the right side and the left side, right? This is credible, and this is actually your highest density region. Okay, so if you look at the credible interval, although the interval contains the same amount of area, but the credible interval does not make sense because, you know, it's only the middle, but you will leave out very high value here, right? This very high density on the left and right. But if you look at the highest density region, then you can see that we are taking the highest density on the two of the modes. Okay, so in the HDR actually make more sense or are more meaningful if you have multimodal distribution. Okay, but the credible interval, as I said, right, is easier to compute and easier to find because we only take, like, you know, the alpha at over 2 and minus alpha over 2 percentile of the posterior distribution. So it's easier to find. Okay, and the credible interval are actually invariant to transformation of the parameter. So this one you're going to see next week, right? So just take note, right? We're going to use transformation for next week. So please brush up on your transformation techniques. Okay. So that is the interval, right? So we'll finish up for this week. Okay, I think I'm not going to finish all of this chapter today, right? So we're going to look at what are the use for this BCI for the posterior distribution. We can also use it for prediction. So similar to frequencies, right? We want to make prediction about the values of future observation. Okay, so if Z is a value of a single future observation, single, right? Single. Okay, and then so Z is an unknown. So if we take the Z as an unknown parameter, right? Then we can actually treat it as a random variable in a Bayesian framework. Okay, we want to find the predictive distribution, which is Z given Y. note that this does not depend on theta. So your predictive distribution actually does not depend on theta. So this is actually a distribution of your future observation given the data that we have observed, which is your y. Okay. Using the laws of total probability, right? So if we have this z given y, okay, so you can see that z given y can be found by using the posterior, sorry, the not posterior, the joint, the distribution of z given the parameter theta. So this one, as I said before, right, because we assume the data is come from the same distribution, then the data z will come from the same distribution as the data y. So we assume they are from the same distribution yi, from which is yi. Okay, so this is the data, and this is your posterior, which you obtain already from the data that we have collected. So this is your data, your future observation given your parameter, and this is your posterior already from the data, using the data. Okay, so your z given y is actually the distribution of the data given theta, but you average. Okay, so this is why you can see, right? Why is there's no theta here? Because we actually integrate or average over all possible values of theta. Okay, that's why we don't have z. We don't in the predictive distribution. We don't have theta. Okay. Right. Just take note. Right. How do we actually get that? We actually get that equation, right? So if you think about it, right, how do you actually get your z given y if you have the joint PDF of z and theta, right? And then you differentiate your theta. Okay. So if you have the joint z and theta, so this is the joint PDF of z and theta given y, and you differentiate your theta, then you will get z given y. Okay, and how do you get? So how do you actually find this z and y, the joint PDF or z and y, the joint posterior or z and y, z and theta? Sorry, this is actually you can get if you have in theory, right? You have the three together, then you have divided by py. Okay, and then this is this z theta y you can get from your conditional, right? Given y, so we have y. So y is a vector. Okay, and then you have and then so this is again. You think this is where you also have to use a lot of conditional probability. So this is P y. Oh, sorry, this is not P theta. Should be Py. Okay, right. So you can see over here. Then if you have the joint for z and theta, then we have the joint for z, theta, and y given by divided by py, and this is you can find the joint z, theta, y with using the conditional for z and theta and y, and then theta and y you can get from the conditional of theta and y with y. Okay, so just so I say, you need all the conditional behavior. Okay, and then you can see you already cancel out your py here, and you are this one, right? And then this is actually equal to pz given theta and p theta given y. Okay, so why is this correct? Because we assume that z and y are conditionally independent. Okay, so sorry, not z and y. Oh yeah, z and y are z and y. Oh yeah, Z and Y are conditionally independent. Yeah. So Z and Y are conditionally independent. So that's why your Z given theta Y is equal to Z and theta. So Z and Y are conditionally independent given theta. So you have this. So that's why you can get your joint PDF or Z and theta given Y is equal to this. Okay, right. Then, so this is actually the easy part. This is actually the easy part because the harder part will be to actually find it, because you can see there's a lot of things going on here. Okay, so let us see, this is actually a generalization of the example that we had last week, right? So we have number of patients surviving to 6 months, but here we don't have data, we only use Y. I mean, in general, it's Y. So this is your data. Y given theta is binomial n theta. Okay, binomial n theta. So this is your data, and then you have a prior, which is theta is beta AB. So instead of the data, the values that we used last week, we're going to use it in a general. We're going to use a general constant. Okay, so if you have the data here, right, and then you can show that you have the likelihood. Okay, so this one I will leave it for you to try. Okay, how to get the posterior in the general way, but it's just the same, meaning that you have your likelihood, which is theta given Y. Okay, so here, you know, right, it's not a vector. Theta 3Y, this is actually your Y plus Y. Wait, let's see. I think. Oh, okay. Right. I think. Okay. So you have your likelihood is theta. Then you have Y minus theta and minus Y. Okay. And your theta is actually your theta. Sorry, your P theta is theta A minus 1 minus theta P minus 1. Okay, so you have your likelihood and you have your prior, and then you multiply it, right? Multiply it, that's why you get the kernel. So the kernel is actually this part, right? You can see the kernel is this part, right? Which is Y plus A minus 1. So you multiply this and this, Y plus A minus 1, and this is Y minus theta n plus B minus Y minus 1. Okay, so what is this distribution? Okay, so this is actually a beta kernel. Okay, and take note that your theta, so in here, your theta is between 0 and 1. Okay, because it's a probability between 0 and 1. So that's why we have a beta kernel. So this is actually a beta Y plus A n plus B minus Y. Okay, so this is the distribution. Let me. This is the distribution of your, this is your posterior distribution, which is beta. Okay, so you can find, you can multiply this, and you can see this is the kernel, right? And then this is the is the PDF, it's a kernel of a beta distribution. So that's why, and this is the kernel, but this is actually your proper PDF for your beta. Okay, so why do we need this? Because we actually need it when you find the predictive distribution. Okay, so then you have a future predictive Z. Okay, so here Z, we have a new data, we have M patients. Okay, we have M patients, so means that we have so number of patients who will survive to 6 months. So Z given theta is now binomial, but with M theta. Okay, they have the same distribution, which is binomial, but it will have a different parameter because this is again Z is actually the sum of the M patients, right? The sum of the, let me say ZI, right? The patients who will survive in the trial of M patients. So this sum is actually binomial M theta. Okay, right. So to find the, okay, so why do I say you need to have the proper PDF? Because if you remember the function, right? The, let me see. You look over here, right? Because this Z is a proper PDF. So this one, they are using a PDF here, not the kernel. Okay. So that's why you have the proper PDF here. Okay. 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 This is what I say, right? Just I think maybe you miss it, right? So to find your Z given Y, you actually use a proper PDF. So this is actually your binomial. Okay. This is actually your binomial. This is your PZ given theta. And this is your posterior, which is theta given Y. Okay, so here this is equal sign. Okay, what happened with this proportional is because this is too long to write. Okay, so what happened here is I just take everything which is Z and theta, right? Keep anything which is with Z and theta, because Z is your Z and then theta you need to integrate. Okay, so but here just keep, so take note that we have a constant which is this one. Okay, this constant here. So if you want to make a proper PDF, you might need to bring back the constant. So what happened here is, you can see over here, right? I take out this constant I take out. So that's why it's proportional here. But the equal sign, as I said before, the equal sign is equal to this line. This thing here is equal to this sign. So this constant actually, even though I take it out, but if I want to make a proper PDF, what happened here is actually you can see I bring it back here. So I bring it to make it a proper PDF. I should bring back the constant over there. Okay, but because it's too long to write, right? I just take it out. So the rest is your MZ. You keep your Z here, and then the theta here I simplify from all the theta inside there. I simplify, right? And then you get this kernel. Okay. So this is going to be a technique in Bayesian, all right, or maybe even in the usual probability is you have to recognize the kernel, and then you can actually, okay, to get it to integrate to one, you must make sure that it's actually a proper PDF of a distribution, because PDF will always integrate to one. Okay, if it's a proper PDF, it should integrate to one. So what happened here is you have to recognize that this is a kernel of a beta. Okay, so how do you recognize, right? Is to remember from before, right? This one, if you have this kernel, here, this is actually theta y sin something minus 1, minus theta sin something minus 1, and then theta is between 0 and 1. So this is a kernel of a beta. Okay, after you recognize it's a kernel of a beta, then this is a kernel of a beta here. Okay, so then what happened here is to integrate, to make it easier, right? To integrate, then you actually recognize it's a beta. So what is this distribution? Okay, this is actually a beta distribution, and this is actually, so okay, and then because when you have a beta, because a proper PDF should have constant also, so it's why you add this one is basically a constant. For example, is a C, right? You add a C here. So this is a C here, and this is a 1 minus C here, right? Because they cancel out. But this constant needed so that this will integrate to 1. So this is actually a beta Z plus Y plus A N plus M plus B minus Z Y minus Z. Okay, so this is a beta distribution. So we have all this constant. Then because you have the kernel already, but then you have to multiply the constant, and then multiply one over constant, right? So this will actually integrate to 1. Okay, the PDF of beta, if a proper PDF will integrate to 1. So then you are only left with the constant here. Okay, right? And then you have here, then you have from here to here is because you should remember that this mz is actually a gamma function, right? This choice mz here is a gamma function. That's why you get from here to here. Okay, and then you, as I said before, you add in back this constant here. This constant here you add back, and then you have this long PDF, which is actually a PDF or PMF of a beta binomial, right, with the parameter n, alpha, and beta. Okay, right. Yeah, it's long. Okay, so the idea here is to do this means that you have to actually integrate, right? And then you have to simplify, you have to edit whatever, and then you have to find the distribution. So yeah, it's long. Okay, so the other way, not other way, the other way is, instead of finding the distribution, right, we can also just find the mean and variance. For example, right, if you want to find the summary of the distribution, we can only find the mean and variance. So you can actually use the property of expectation, right, which is the conditional expectation and the conditional variance. Okay, so then for the previous example, what happens here is we want to use the conditional mean and variance to find the predictive mean and variance. Okay, so if you have your Z, is binomial m theta. Okay, then the expectation. So this means you only need to know the mean and variance. Okay, simpler, but still need a bit of algebra also. Okay, and then you have theta given y is beta. Okay, so if it's long, right, you can always use a simplify notation because it's too long. For example, I use alpha and beta, right? And then I have my mean, and then I have my mean of my posterior would be, okay, the variance is long actually, but variance for beta is long. That's why I use alpha beta, because even with the alpha beta is long. Right. Okay, right. So this means that we have the distribution of your Z and your data, new data, and the posterior for the old data. So you have, okay, so this means that you need to know the mean and variance for the binomial, and this is the beta. Okay, I don't expect you to memorize, because there's a table. Yes, now remember there's the table that I've given you about the distribution. It's also the mean and variance for the distribution there. So you don't have to memorize. Okay, but you have to know the distribution, right? And you have to know the technique. Okay, so then using this is, you need to use this identity here, the conditional identities. Okay, first the mean is usually easier. Then you have the variance, which is harder. Okay, wait, I need to move it. Okay, right. So the mean, the predictive mean. Okay, then you have the y. Let me write first. Okay, so here, right, if when I want to find the mean, okay, what happened? Okay, didn't, right, okay, right, okay, so to find the predictive mean, right, is that given y? So we have to find the expectation of the z given theta, but based on the posterior theta given y. Okay, so the expectation of z given theta is m theta. So m is a constant, that's why you can take out the m here. But then the expectation of theta given y for theta is actually your posterior expectation. So because theta is your beta, so it's going to be the mean of your beta distribution. Okay, so that is the mean. Okay, so usually the mean is actually the simpler part. Okay, and then you have the variance. Right, the variance is going to be expectation of the variance plus the variance of the expectation. Right, so okay, when I do this is, okay, why do I actually put it down here? Because this means the mean of the posterior and the variance of the posterior. Okay, right, and then the expectation is against that posterior distribution, which is if your posterior is beta, then it's against beta, right? Beta, then you have your variance. Okay. All right, this is going to be long. Yep. Can I move it? Oh, no. Okay, this is the problem. When writing here, oh, where's the maximum already? Okay, how many page do I have? Oh, is there? Okay. Wait. Okay. All right. So I'm not going to finish it because it's going to be very long. But okay, so the idea here is just let me share with you, right? Okay, so the idea here is if you have the function, so expectation of the variance plus the variance of expectation. So for the variance of the z given theta, so that is a binomial. So we have the binomial variance. So this is the binomial variance. So expectation of theta given y. So the theta is actually a beta. All right. So that's why you get here. Um, Okay, but before that, then we have the variance of the expectation of Z. So the Z is binomial, so the expectation is M theta. And that's why, and the variance, M is a constant, so you take out M, become M square, and then you have variance of theta. Okay, so variance of theta, and then the posterior variance, so theta is your beta distribution. Okay, so one thing here, okay, one thing to take note, right? If you're doing this part here, you cannot do it directly because this is a function, but so you have to break it up, right? So you have theta here. So this is actually going to be theta minus theta square. Okay, minus theta minus square. That's why you get expectation of theta minus expectation of theta square. So separately. Okay, so expectation of theta is fine, but expectation of theta square is not there. So you actually use this notation, right? Variance of x is actually expectation of x square minus expectation of x squared. So you use this identity or this value. That's why you get the expectation of theta squared is actually variance of theta plus expectation of theta squared. So that's how you get it. Okay, and then after this, then you can put in. So here, the posterior, then you can put in the values here from here, which is the mean of theta, the posterior mean and the posterior variance, right? And you can actually put inside this equation and you can get the answer. Okay, it's too long for me to write. It's a bit too long for me to write, so you can do that and then you can simplify at the end. Okay, right. And what's the end? I think, oh, right. Okay, so after, okay, that one is you find the mean and variance, but after you found the predictive distribution, then we can actually use it the same way as we use a posterior distribution, right? For example, we can calculate a 95% predictive interval, right? So for example, in the example, if you have a data which is normally distributed with unknown mean theta and non-variance sigma square, and we have a prior which is also normal, then we can find the posterior. So we have found the posterior distribution before. Okay, and this one is also, I think is one of the question. We can find the predictive distribution for when it's normal, and it's also okay, so the posterior the predictive distribution for z given y is also normal, right? And you can see that the weight is actually this is actually your posterior mean. Okay, so you still have this posterior mean, the same posterior the same mean as before, but actually you have different variance. Okay, the variance for the data, so you can see this is actually the variance for z, the data z, because z is a normal, and this is actually your posterior variance. Okay, and to show this, then it's going to also be long, right? So I'm not going to go. I think this one of the also one of the exercise actually. Okay, so I think that's the end for today's